All right, getting into our next lesson here on triangle or figure similarity, looking at dilations, comparing similar figures, congruent figures. Starting off with this warm-up, describe at least two different single transformations or sequences of transformations that map figure A to figure B. Well, looking at figure A and figure B, my first thought would be rotation based on the orientation and how it's rotated around from the second to the fourth quadrant. So I believe we can probably try first to rotate this based on one transformation, and it would be a 180-degree rotation since it went around two quadrants to get from quadrant 2 around to quadrant 4. And if we test that out, you're going to find that that is correct. So if we check, let's say this point here, let me get my pen to work. To there, the original figure, called figure A, that point is at -6, 0. And our 180-degree transformation rule tells us we are going to take point x, y, and it's going to become -x, -y, as it rotates around. So if we compare that to where it ended up, it should be at 6, 0, and it is. And we can check that with the other corresponding points too. If we check these two, the original in figure A there is at -7, 4. And if it's rotated 180 degrees, we should find it at 7, -4. And that's exactly where it ends up. And you can test the other points too. They will both, you'll find the same thing with the last 2 points. They will have followed a 180-degree rotation around the origin as our center of dilation. All right, moving on to the next page where it says getting started. Just looking at comparing similar figures or congruent figures. It says often we say the dilations preserve shape and rigid motion preserves both size and shape. So remember, congruent, we're preserving size and shape. Angle measures and side lengths stay the same. The difference with similar is that we maintain the angle measures, which maintains the shape, but the size changes. So if we're looking at number 1, if you measure those side lengths and angles, you would find they are congruent. We got same side lengths, same angle measures, size and shape. Compared to 2, the size has changed, but the angle measures haven't, so those would be similar. Also with 3, same thing. We'll find obviously they're not congruent, different size, but they are similar. The side lengths would be proportional to each other. And we'll find the same thing with 4. Not only it's similar, they've taken that figure, made it smaller, dilated it smaller, but it's also had a rotation too, but it is similar if we measure the side lengths and see that they are in proportion to each other. Okay, I'm going to skip down to 6, and we would see if we measured those side lengths, say from here to here, that's going down 2 units, right 2 units. But if we compare here to here, 1, 2, 3, right 2. So the change in size, the dilation hasn't been equal among all the side lengths. That change doesn't represent a proportion among the other side lengths either. So that one, number 6, would not be similar. Okay, easier to tell when we have those coordinates on the grid. That's why I skipped past 5. If we could measure those, if I had a way I could put a ruler on the screen, you would see that with 5, they are proportional to each other. So those are similar. Okay, but main key takeaway is that similar means we maintain the same shape, the angle measures stay the same, but they're not congruent. The size has changed. All right, determining similarity. So to be similar, we have to have a proportional dilation among all the points in that figure. So if we check A here, the 2 triangles, that first graph, if we want to compare them, we would find corresponding points. Let's say A and D. I'm going to start. Let's start with the bigger one, A. We'll say that's the original triangle. So point A is at 3, -3, and the corresponding point, point D, we'll find is at 1.5, -1.5. If we now check C and compare that to corresponding point F, C is at 8, -3, and corresponding point F is at 4, -1.5. Okay, and then the last point, point B, is at 8, 3, and corresponding point E is at 4, 1.5. And what you'll find if we compare all those to get from the original point to the new point on each one is we've multiplied each X and Y value by a half. The easiest one to spot would be on point C and point B. To get from 8 to 4, we multiplied by a half. Same thing on B. Once you have a hypothesis on that with the numbers like 8 and 4, you can test it on all the other numbers. And something like, say, the Y value on point A, -3 times 1/2 will give you -1.5. And the same thing for the other two Y values. So we have had a proportional ratio applied to all of the points, dilated by a scale factor of 1/2. So these are similar. Okay, if we check B, start with red again. Mark these 2 points. This time, let's say the smaller one is the original one. So that point N is at 3, 0, and the corresponding point A is at 12, 0. And then if we check point W and K, so point W is at 3, 3, point K is at 12, 12. And then one more, point P and G, those corresponding points. Point P is at -1, 1, and G is at -4, 4. So if we compare all those points, let's take the X values on that first one, for instance, 3 to 12. Well, what can we multiply 3 by to get to 12? Well, it would be times 4. Okay, well, let's test that with the other ones. Works with point W, 3 to 12 times 4 on both X and Y, and it works on point P. -1 times 4 would be -4 for the X values on point P to get to point G, as well as the Y values. So we have a scale factor of 4 on each point, so those are similar. And for figure C, we're going to find that they are not similar. If we just take one point, for instance, let's say point J. Point J is at 1, 4. Well, the corresponding point, point K, is at 2, 8. Well, to get from 1 to 2, for the X value, we did times 2. And if we get from 4 to 8, that's times 2. So let's check another point. Let's go from, let's say, point G and the corresponding point, point D. So point D, start with the smaller one again, is at 5, 1. Point G is at 10, 1. Okay, well, we multiplied 5 times 2, just like the other point, to get to the value of 10. But for the Y value, 1 stayed 1. So we have not had the same scale factor applied of 2 amongst all points. So these are not similar. Okay, so that's how we can use dilations to determine whether figures are similar. Okay, moving down to point D, I'd say pause the video. I want to see if you can try this one out, see what you come to a conclusion on, and then unpause it so you can check your work on that. All right, well, if we do test this one, you should have found that these are similar. Point Z corresponding to point F, and that is multiplied by a scale factor of 2/3. 2/3 of -6 will get us a -4. And you'll find the same among all the other points. So we got we'll check one more. Point N from 12, -3 to point B, 8, -2. You'll find the same thing. 12 times 2/3 will get you to 8. -3 times 2/3 will get to 8. So these should have been found to be similar. And you'd find the same for that last corresponding point there as well. All right, so proving similarity through transformations. So now we're going to see if we can transform these around to not only dilate them, but get them aligned through other translations, whether they're transformations, whether they're translations, rotations, reflections, anything of the transformations that we have learned. So it says triangle MAP is the image of triangle QRN. So the original is QRN. After undergoing at least one transformation, determine the possible sequence of transformations. Well, the first thing I would say is let's look at a rotation. It looks like that figure, if we're starting in that first quadrant, has rotated around. So that would be my first test. So if I take the points 5, 7, 7, 7, and 7, 1 from that original figure and rotate it 180 degrees, the 180-degree rotation rule is -x, -y. So that point would become -5, -7. The next point would become -7, -7. And the third point would have become -7, -1. Okay, from there, it's obviously gotten bigger, so we need to figure out a dilation we've had happen. So if we look at the points on the new figure, for instance, we've gotten to 14 from 7, if we look at these corresponding points. So my guess would be, to test out the hypothesis, we've multiplied by a scale factor of 2. So if we multiply by a scale factor of 2, we are going to end up with this point being -10, -14, this point being -14, -14, and this point being -14, -2. And if we go compare that to our points, we're going to find that's exactly the points we've ended up at. So they are similar, same shape, size has changed because of that dilation, but they are not congruent. Okay, C would reverse order of the transformations described. What would you notice? It would map to the same figure. Remember, the order we do the transformations in does not matter. Map to same, I left off the word there, to same figure. Trying to talk while I write at the same time. All right, 2. Triangle XYZ is the image of triangle ABC. After undergoing at least one transformation, list the corresponding sides. Well, first thing I'd look at is the side length. So for instance, on this triangle, the smallest side is 2.9, and the smallest side on this one is 5.8. So my guess would be, if we're going to try to match up corresponding sides and angles, those sides would correspond. So imagine if this one was flipped over, so that side corresponds with that side. And what we would find angle-wise is angle A corresponds to angle X. So A to X. Angle B corresponds to angle Y. And angle C corresponds to angle Z. And then for side lengths, like I just mentioned, AB would correspond to XY. BC would correspond to YZ, and CA would correspond to ZX. And there would be our corresponding sides. So a sequence of transformations, well, I just said it's reflected. If we had a line between these, it'd have to be reflected for that side of 2.9 to match up with the side that's 5.8. So it's reflected. And then also, if we look at the scale factor, 2.9 times 2 would give us 5.8. If we look at the other side, 3.25 times 2 would get us to 6.5. And 5.05 times 2 would get you to 10.1. So it's dilated by a scale factor of 2. And again, with the reverse order of the transformations, what would we describe? It would map to the same figure again. The order does not matter. All right, triangle ABC was dilated to create new triangle ABC. The triangle ABC, the new image, was dilated to create another new image, ABC. Describe a series of transformations that map it. So we're starting with that bigger one. And if we look at that, it has obviously gotten smaller to create that first new triangle. So we call this original, second one. Here's our third figure. So if we look at the scale factor, just looking at points A, if we know they're similar, original point A is at -6, 4, and the new point A is at -3, 2. So we can see each one of those are half of the original. So it's dilated by a scale factor of a half, and then to get to figure 3, it looks like we have just translated down. We have slid it down. And that move down is 1, 2, 3, 4, 5 units. So it's dilated by 1/2, scale factor of half, and then translated down 5 units. Moving on. So for number 5 here, it says use the dilations and other transformations to determine if the triangles represented by the coordinates are similar. Okay, again, this would be a good time now that we've gone through all the different dilations and transformations. Pause the video, test your hypothesis on each one, and then unpause it just to check your answers. So for 5, for instance, you should find that yes, they are similar. And if we want to figure out what the changes were, what the transformation, dilated from the original figure of ABC by a scale factor of 2.5, and then reflected across the x-axis. So after you dilated, you should have used the rule xy has now changed to x negative y, reflected across the x-axis. B, you'll find that no, they are not similar. And the reason they're not similar is, for instance, points K and L are dilated by the scale factor of 1/2 from the origin, but J is not. Okay, point J should be at -3.52. 3.52. There we go. And it is not. So they're not similar. All right, and then C, when you test C, you should find yes, they are similar. And you can dilate the original triangle ABC from the origin as the center dilation by a scale factor of 2. So dilated by a scale factor of 2. And then you can translate the triangle 13 units to the right. So translated 13 right. So that would be a translation rule of xy becoming x plus 13y. All right, a little more comparing images here. It says the labeled figure is the pre-image to create the other 2 figures from the dilation, determine the scale factor, and map each one. Okay, so if you test those, again, I'm gonna let you try to pause it and test your hypothesis here on your scale factor to compare the figures. And you should find that from the original figure, which is like that medium-sized one, to get to the bigger one, it was a scale factor of ×2. To get to the smaller one, it's a scale factor of ×1/2. So pick out your points there, test that, make sure you can match up the points using those scale factors. Are they similar? Yes. If they are dilated by the same scale factor, if they're dilated by the same scale factor, they are similar figures. Okay, it says triangle HUB was dilated from the origin by a scale factor of 2/5 to create the new HUB, and HUB is congruent to TAP. So what's the relationship between HUB, this triangle, and TAP? Well, if it's similar, HUB is similar to the, HUB is similar to the new HUB, the pre-image is similar to the new one, that means it is similar to TAP when it's translated up. So they are all similar. And the sequence of transformations you should find after dilating by that 2/5 that they told us, it is translated up 1, 2, 3, 4, 5, 6, and left 2. So up 6, left 2. So that translation rule would be x minus 2, y plus 6. Okay, triangle DOT was dilated from the origin by a scale factor of 3 to create the new DOT. The new DOT is congruent to JAR. Determine a possible sequence of transformations that maps triangle JAR onto triangle DOT. Okay, again, I'd pause it, test your hypothesis, unpause it, see if you can match up to what our answer is here. Okay, what you should have found is first thing you notice is that rotation to get from this figure to that figure. It's been rotated around. So we have a rotation of 180 degrees. It's moved around 2 quadrants. And then it's scaled down, and if you test your points, corresponding points, it is scaled by a scale factor of 1/3. And they are similar to map those two figures together. All right, so wrapping up, triangle ABC is dilated 4 times with different scale factors. The 4 images are congruent. Is that true or false? Not true. Remember, dilating changes the size. Congruent has to be same size, same shape. So we could say not same size anymore. Okay, triangle HIP is dilated by a scale factor of 8, followed by a scale factor of 0.25. The final image is congruent. Again, if we dilate it by a scale factor of 8, and then a scale factor of 0.125, if you were to find out what fraction that is, you could use your calculator, it is 1/8. So basically we have reversed the original dilation and we end back up at the original figure. So yes, those are congruent. And then last two here, dilations are used to create congruent figures. Nope, dilations change size. Congruent figures need to be the same size and shape. Transformations are used to create similar figures. This is always true. Any of our transformations we are talking about maintain similarity, but only some maintain. Only rigid motion transformations can maintain congruency.